We often perceive information technology as a weightless, invisible force living in the cloud, but beneath that clean aesthetic lies a massive physical infrastructure. This physical architecture carries a compounding ecological debt across every phase of its existence. This chart isolates the baseline environmental impact of the information and communication technology sector. Currently, ICT infrastructure accounts for roughly 2.8% of global greenhouse gas emissions. Integrating the full supply chain and the extraction of raw materials pushes that share to nearly 3.9%. Global digitization is accelerating this trajectory as billions of IoT devices, wearables, and server farms come online. Treating the environmental cost of electronics as an afterthought invalidates the efficiency gains achieved by the software they run. For decades, hardware engineering focused on a triad of optimization, maximizing performance and functionality while minimizing immediate cost. This diagram outlines the transition to a modern eco-design framework. The top row couples sustainability directly with high-performance hardware. Production cost is now tied to the device's lifecycle impact. Finally, functional design must accommodate recyclability. Modern hardware engineering requires solving a complex optimization problem governed by hard planetary boundaries. The life of a circuit begins in the geological extraction of raw resources. This map breaks down modern material consumption. A smartphone requires dozens of periodic elements. Precious metals like gold and palladium are required for stable conductivity, while rare earth elements like neodymium are used in vibration motors and speakers. Other rare earths like europium and terbium are mandatory for display color generation, while lanthanum stabilizes camera lenses. This creates a fragile global supply chain, with 85 to 90% of rare earth refining concentrated in China. The extraction process relies on aggressive chemical leaching, which creates toxic runoff and radioactive tailings. Most of a device's ecological debt is incurred in the dirt, long before the components reach an assembly line. From the mine, these materials move into the hyper-controlled environment of a semiconductor fabrication plant. Despite their microscopic scale, semiconductors are among the most resource-dense objects ever manufactured. This visualization compares a microchip to its manufacturing footprint. Producing a single chip consumes over 200 liters of ultra-pure water. The process is also chemically intense, requiring hazardous substances for silicon doping and PCB etching. Once deployed, these chips sit in data centers like this, requiring a continuous, massive power draw to stay online. Standard metrics like power, performance, and area are incomplete because they ignore this massive upstream and operational footprint. The ultimate failure of a linear tacheconomy is the downstream accumulation of discarded hardware. This infographic details the scale of the problem. We generate over 62 million metric tons of e-waste annually. Globally, only about 17 to 20% of that waste is properly recycled. This compounding crisis triggered a regulatory response in the early 2000s that rewrote the rules of hardware engineering. This timeline focuses on the introduction of the RoHS and WE directives between 2000 and 2003. We mandated producer responsibility, formalizing take-back and recycling systems for all electronic equipment. RoHS went further, banning toxic heavy metals like lead and cadmium from commercial devices entirely. These directives physically remapped the industry, outlawing decades-old practices like lead-based soldering effectively overnight. The old workflow, where an engineer finalized a schematic and ignored its eventual disposal, is obsolete. This flowchart illustrates the modern compliance path. Environmental standards now dictate the earliest stages of product development, starting with material selection to verify the absence of hazardous substances. These initial choices are tied directly to the final requirement, end-of-life compliance. Solving for a device's disassembly and recycling is now just as critical a design parameter as optimizing its clock speed. If we view the entire macroeconomic system of technology production, the need for a structural shift is clear. Infinite technological growth built on finite raw materials and a linear disposal model is a physical impossibility. This animated loop demonstrates the structural solution, engineering a completely closed-loop circular system. Green electronics is an interdisciplinary field, requiring mastery of electrical design, industrial chemistry, and supply chain logistics to maintain this loop. Embracing this framework reduces long-term economic risk and drives a new class of material innovation. Engineering excellence is now defined by achieving these technological marvels strictly within the boundaries of planetary sustainability.